Imagine a world where you would deliberately introduce trigonometric functions where you didn't have any before in order to solve a problem. It sounds crazy, but that's exactly what we're going to do. We're on our way to being able to solve an antiderivative that looks like this. That's pretty gross. Let's set integration aside for a second and let's just talk about simplifying things. This expression right here, hopefully you would agree that that's actually not so bad in terms of simplification, right? Because first of all, I can factor off a 9, and if I do that and then let the square root do its job, this expression would simplify to 3 times the square root of 1 minus sine squared theta, and that 1 minus sine squared theta is just cosine squared theta because of everybody's favorite trigonometric identity. And the square root of cosine squared is just 3. Well, it's just cosine theta, and then we still have that 3 dangling in front. So, kind of gross, but not too bad. Then we come over here. Everybody wishes that this would simplify to just 3 minus x, but it doesn't, and you know that it doesn't. However, if you look at this and look at this, you might say, well, golly, I wish that there was a trigonometric function sitting right there, in which case this would simplify very much the same way that does. And whenever you start thinking, gee, I wish that something could be in that place, well, you just remember in these math expressions, I am in charge, and if I want something there, I will put it there. We just have to do it properly. So what I would really like to make happen is to say turn this into a squared term that actually has a sign instead of an x, and maybe that I can generate a 9 in front of it, in which case it would look exactly like this and it would simplify exactly the same way. And I can do that by making this substitution. If I think to myself, I wish that x was a 3 sine theta, I can make that substitution. And if I do that, then I have the square root of 9 minus, if x is 3 sine theta, x squared is 9 sine squared theta. And now I've converted the expression that I have into something that looks worse, but only temporarily because it would simplify just like over there. So we do have structures where the introduction of a trigonometric function counterintuitively actually helps a lot. The other way this might work is if I'm involving tangents instead of sines and cosines. Everybody remembers we have sine squared plus cosine squared is 1. We also have tangent squared plus 1 equals secant squared. That's the partner identity. So this particular expression looks kind of gross. That's a theta, by the way. Looks gross, but simplifying, if I factor off of 4 and then let the root do its job, I can pull a 2 out front and have left tangent squared theta plus 1 on the inside. And then I remember my identity, the tangent squared plus 1 is secant squared. And this particular mess has simplified quite a bit. So then, maybe I'm looking at something that has this shape, and I'm thinking, wow, look what just happened over here. Gosh, I wish that this was a tangent squared, or even better, a 4 tangent squared. Well, to make it a 4 tangent squared, a nice substitution like x equals 2 tangent theta, if I make that substitution, x squared will become 4 tangent squared theta. And so with that substitution, this radical expression can be made to look like this, which then simplifies to 2 secant theta. We're going to use this idea in the context of an antiderivative. So I'm going to move this out of the way. I'm going to come up here. And I'm going to say to myself, golly, I don't know what to do with this yet, but thinking about what just happened, man, I wish this was a sine squared theta instead of just an x squared, because then this radical would actually simplify. So let's see if we can make that work. I would just like to, in this case, trade my x for a sine theta. And if I do that, that radical expression will turn into root 1 minus sine squared theta, and maybe you can see where this is going. However, since I'm doing an antiderivative, not only do I have x, but I have the dx to deal with. So if x is sine theta, dx needs to be cosine theta d theta. So with dx needing to be cosine theta d theta, let's just load it up with a direct replacement. Out here, x cubed, well, here's my substitution, x is sine theta. And so I've taken this, which looks horrible. I've actually deliberately introduced trigonometric functions like a crazy person. It made this horrible, horrible looking thing, but watch what's about to happen. Remember that the reason we did this substitution was that that radical is now the square root of cosine squared, which is just cosine theta. And then out here we have cosine theta d theta. Or, mushing this up, we have that. And so what we've done is we've converted this antiderivative of a radical expression into a trigonometric integral like you did in the previous topic. This one, hopefully you remember what to do. I have to decide what kind of regular old u substitution I might put in play. I'm going to remember that if I pick u equals cosine theta, then one of these sines, sine theta d theta, will become my du. Right? If u is cosine, then du would be negative sine theta d theta, or negative du is positive sine theta d theta. And so one of these three sines, along with the d theta, will become negative du. This cosine squared will be u squared. And I used to have three sines. One of them has gone over with the d theta to turn into du, so I have two sines left. And sine squared is 1 minus cosine squared, like this. That was very fast, but we're now reviewing the previous topic, so I don't want to take too much time. Multiply everything out. Oh, what the heck. Let's take care of that minus sign now by reversing the order of subtraction. And now we've got a couple of power rules. Ta-da! But remember, we're not done. This substitution right here was u equals cosine theta. Ta-da! Oh, but darn it, we're still not back to the original variable, are we? Oh man, the original variable was x. We did one substitution called a trigonometric substitution to turn the nasty problem into a trigonometric integral. That's not as bad as it was. That trigonometric integral involved a regular old u substitution. So we solved it. We reversed the regular old u substitution to get back to here, but we haven't reversed all the substitutions. We still need to get back to x. And, aha, just to make it worse, the substitution was x equals sine theta. We're looking at cosine thetas. How in the world are we going to return the thetas back to x's? Well, it's all about geometry. I'll draw a triangle. If the sine of theta is x, that means the sine of theta is x over 1, which means if this is theta, here's an x, and here's a 1. Which then means that this side, by the Pythagorean theorem, is the square root of 1 minus x squared. And that means that the sine of theta is x, means that cosine theta is adjacent over hypotenuse, square root of 1 minus x squared. If you know one of the trig functions in terms of the ratios, you know all of them. You just have to dig them out. And so finally, we can go back to our expression, and cosine to the fifth is this thing to the fifth. Ugh, yuck. And then cosine cubed is this horrible thing cubed. And if you would like, you can make some fractional exponents out of that. Squish this up a bit. So there's an exponent of 5/2 on the 1 minus x squared. A fractional exponent of 3/2 in the next term. And then we're done. This is trigonometric substitution. Taking an antiderivative that has a radical expression in it, where you look at that radical expression, you say, man, if only there were trig functions in this, because if there were, the square root sign might actually simplify away. So you implant the trig functions that you need to make that happen, and you turn it into a different integral. And then you look at that integral and you say, oh, I know how to do this. I don't like it, but I know how to do it. And so you do that integral this way, and then when you're done, you have two substitutions to reverse, not just one. Isn't calculus fun?